What is the internet? On Wikipedia, it's defined as a global system of interconnected computer networks that use the Internet Protocol suite to communicate between networks and devices. So the first part of this definition is essentially the internet is a network of networks, and it links all these networks by electronic, wireless, or optical networking technologies. And then it uses the Internet Protocol suite, so TCP and IP, and it routes packets in accordance to these protocols. So I'll be going over mainly this for the next few slides. And then it's to communicate between networks and devices. So talking about private, public, and all these different types of networks. And its main job is just to move data from one place to another. First of all, what's a protocol? We just talked about how it routes packets in accordance to these protocols. So protocol is nothing more than just an established set of rules to determine how data is transmitted between different devices over a network. For example, you have HTTP or SMTP. HTTP for like websites, SMTP for emails. There's certain rules regarding how devices communicate with each other. And the main two that we'll be focusing on are the transmission control protocol. So this is for sending packets across internet, and it's supposed to ensure the successful delivery of data. And then there's the Internet Protocol, which is IP, and it describes how computers should route information. And you'll see that under these two models, there are several different types of protocols. So in our application, there's SMTP, this is email, file transferring, FTP, HTTP, and so on. And these are all different protocol stacks. Okay. So more about those models. So this is the OSI model, Open Systems Interconnection Model. And it's a conceptual framework that describes the function of a networking system. And it's basically just abstracting it so you don't have to worry about the implementation details, and each layer doesn't have to worry about how the other layers function. It splits it up into 7 main categories. Created in the 1970s when networking was taking off, and there were 2 separate models that merged to create this one. So you'll see that down here in the physical layer, it concerns mainly transmitting raw bit streams over the physical medium. Then in the network layer, it's deciding what the path it will take, which routers. And there's a data link layer that links these two together. And there's a transport layer, and you notice that it uses these protocols. Session layer, presentation layer, application layer. So this is more complicated than we need it to be. There's another model called the TCP/IP model. It simplifies, it focuses on the transport and network layers. So 7, 6, and 5 become application. And all this is it represents the data to the user. And then encoding and dialog control. 4 is transport. So this is supporting communication between various devices. Network determines the best path through the network. And 2 and 1, we just call it network interface, controls the hardware devices and the media that makes up the network. So each layer doesn't have to worry about how the other layers function. This is just a conceptual model, so you don't have to worry about how it's implemented.
Yeah, just like as an example of abstraction, right? Like when you write code, you don't have to worry about how the transistors in your computer are like flipping on and off when you write code, right? So essentially, when you write code, you assume that your compiler knows how to convert that to machine code, and you assume that your computer knows how to run the machine code, right? So in this, like when we're designing like TCP and stuff, we assume that the network knows how to send packets, right? But TCP like assumes that everything below it works, all the physical stuff, all the networking stuff works, and all we have to worry about is making sure that our TCP or IP protocols actually do what they're supposed to.
Yep. Okay, and TCP. Okay, so we'll talk about the TCP IP protocol suite. So these are open standard protocols, which means that it's open standard, so that basically devices from different manufacturers can interoperate successfully. There are such things like proprietary protocols where companies develop their own protocols, and those can become open standard after a while. But the main point is that TCP, part of the transport layer, it's responsible for reliable communication between processes running on different hosts. And and it manages individual conversations. So that's the main point here. While IP, which is the network, it will receive the message segments from the transport layer. So the transport layer will have be breaking up the messages into segments, and then what the network layer does is it packages them, it encapsulates them into packets, and then it addresses these packages. So over here, we'll see that a long message will always be split up into message segments, and then it goes to the network. And what's happening is that this payload is that segment, and what IP will do is it will address this packet. So this is a packet, and there's the sender IP address and there's the destination IP address, along with a bunch of other fields. For example, time to live and the checksum to make sure that nothing's been corrupted. Okay, now talk about the transmission and encapsulation. Okay. Ethernet will transmit the IP packets over a physical medium. So this is concerning this bottom layer here. And the Ethernet, it's called a frame. And inside the Ethernet frame will be an IP packet, which will be a TCP segment. And then inside there will be the user data. And you know, this is clear through the layers. So the application layers on top takes the user data and it adds an application header to it. So that's the application layer. So that this might be like an HTTP header. And then down here, we'll add a TCP header. So this is the message segment. And then remember what happens to segments? They get encapsulated by the IP encapsulates them into packets. So here's an IP packet. And then down here, you'll have a full Ethernet frame, which will be sent through a physical medium. And we call these protocol data units. So we start off as data, which is the application layer. Then we go into a segment, and the message is broken up into segments. Then it's called segment. Then it's called a packet. Then it's called a frame. And then it's called bits at the end. And that's for each layer. And inside a packet header is just metadata along with, like say, addresses. So what's a packet routing network? So now we know what packets are and how they work. Basically, the point of this is that networks have to route packets from the source to the destination. And we use routers for this, which are specialized computers. And when you go from one router to another router, that's called a hop. And a list of hops between you and host, you can find that through the trace route command. And IP is in charge of how routers forward these packets based on the address. So which path to take. And then these routers originated in the 1960s as ARPANET, which was a military project for a decentralized computer network. So those are the first routers, and then internet service providers own their routers, like AT&T and Verizon. So here you can see when I'm trying to go to I'm trying to reach google.com. Here's the list of hops. So you'll see the first hop is to this IP address, and this is my router. This is my public router, which goes from my computer to the public network, and here are a bunch of other routes, and so on. Okay. So packets arrival. Okay, so packets aren't guaranteed to arrive in order or at all. And what TCP headers do is that they prevent packet loss by TCP headers will contain information. Okay, sorry. When the packets arrive and say they're out of order, right? The TCP headers, since remember TCP is in charge of managing individual conversations, they'll contain information on its relative position to the other segments. And every now and then, an acknowledgement will be sent back. Right, an acknowledgement will be sent back to show, okay, we have these packets and we don't. These are the packets that we received, and then we can do a packet retransmission if TCP realizes, oh, a packet was dropped in the middle. And why will the packet get dropped? Well, if a router receives more packets than it can process, it will have to drop some. So TCP headers contain this information to carry out the job of managing a single conversation. Let's talk about IP addresses. So we're talking about how IP addresses those packets. Now there's two standards for IP addresses. There's IPv4, which is probably the one you're familiar with. And there's 32 bits to this, so it's around 4 billion addresses. And recently, well, not that recently, the newer one is IPv6, which has 128 bits. It can hold a lot more, it has a lot more potential IP addresses. So currently there's 8+ billion network devices. And how is this possible when there's only 4 billion addresses? Well, they've reserved private IP addresses. Not all devices need to contact, not all devices need access to the public. And the private IP address will be 192.168. In XX. And these X's are numbers between 0 and 255. So these are the reserved address spaces for private IP addresses. And then the Internet Task Force proposed IPv6, which has 2 to the power of 128 because it's 128 bits. And we're slowly making the transition over to IPv6. It's still going to take a long while before we fully transition. So IP addresses can be broken into 2 parts, a network prefix and a host identifier. You'll see that 129.42 is a network prefix to this, and 13.69 is the host identifier. The point of this is routers send all the packets of this network prefix to the same location. You don't have to memorize where each IP address goes. You just need to know where the network is. Because once you send it to the network's own router will do the job of sending to the specific host. And there's a whole lot more on this. There's a lot more information about subnetting and whatnot. Basically, the point is the number of bits you reserve for the network will take away the number of hosts you have. So let's say if it was one network, you could have that many hosts. But if you had several different subnetworks, each subnetwork will have less hosts because you use a bit for the network splitting up. And real quick, between the private and the public IP addresses, when we translate, that uses something called NAT, which is Network Address Translation Protocol, and that's just something else to keep in mind.
I think Albert had a question about can you trace location through IP? I'm pretty sure every time you get a new router, you get a new IP address. So technically, I don't think you could trace location. Mason, do you know? Like, I feel like if you just like throw away, like, unless they know.
I think there's like a generally correct way. I mean, it's generally correct. You can look up the location of an IP address, and you can generally get the correct area, but obviously, it's not accurate or foolproof in any way. Because I remember one of my friends said you could search up, and I did search up an address to find the location. Okay, the next is domain names to IP address. So this is just when you search up a site called like google.com, you're resolving the IP address. You're looking up the IP address of the human readable domain. So the human readable would be www.google.com. So what your computer will first do is it will check the DNS cache to see it stores recently visited websites. And then it will query, if it's not there, it will query your internet service provider's DNS server. And then it will query the root name servers, which can resolve in every domain. So a root name is, for example, you have .org, .com, .net. And this is like the last step.
Yeah, like basically the way that like accessing websites work is that you send a request and then they send you back the HTML code and then your browser displays it, right? So essentially, in order to get that HTML code, somebody needs to be responding to you, right? So essentially, every website runs on a computer, and those computers have IP addresses. So essentially, the whole point of this is to take your URL and find a computer that's running the website, so that you could contact that particular computer, and it'll send you back the information. So I think if you go to like that website, it's pretty interesting. Should we just demo it for them? That'd be cool.
We want to try google.com.
Hey, why not? might not be as interesting. Well, okay, yeah. Go to trace, I guess. Trace is more interesting. Yeah, so you can see it first like looks for the root server, which basically is like will tell you then where to look for. It's google.com, right? So then it'll look for .com servers, right? And then like I think if you scroll down, it'll eventually talk about the next type that it looks at. There's a lot of root servers, I think. If you yeah. So then see it goes to .com, right? So these are all .com servers, and then these .com servers tell you where Google is located. And then once you have google.com, then you could just ask the google.com for um, to give you the HTML code. Like if you did like eeks.berkeley.edu, then it would first find the edu, then it will the edu server will tell you where to find berkeley.edu, and then it'll send, and then that will tell you where to find the eeks.berkeley.edu servers.
Okay. Next is SSL and TLS. So when you're sending data, there's no way to make sure it's secure unless you use, sorry, it's not secure by itself through TCP and IP, right? But with SSL, secured sockets layer, and transport layer security, you can do encryption and authentication. So for encryption, it's even if a hacker intercepts packets, it can't reconstruct the original message because it's been encrypted. And SSL certificates are just to make sure authentication. The client can trust that the server is who it claims to be. What this prevents is man in the middle of attacks where you're talking with the server, you're giving it information, and then there's a man in the middle, say hacker, that cuts in your conversation and claims that they're the server. Then you end up sending information to them. So you want to make sure the server you're talking to is who it claims to be. And you can see over here that modern day browsers will let you know if a certificate is valid and whatnot.
Yeah,
So why do
well, yeah,
you can
for
talk.
this one, it's kind of interesting because I know Mason already said like it's not secure, right? Like, but it's actually really really easy to sniff packets in your in your network. Does anybody know what your like local network is called? Like the three-letter abbreviation for your house's network is? Anybody know? Okay, well, it's basically LAN, local area network. That's what a LAN is. That's why some people call their servers like WLAN or whatever. But basically, the point is, I literally just downloaded this thing called Wireshark, and I could see all the packets that are going to and from my router. So let me just show you guys real quick. Let's see if I could do that.
Just stop sharing screen.
Yeah. Okay. All right. So basically, there's a Wireshark. You literally just click that button, and hooray! Now you can see all of these packets coming in. There's two different types of protocols, right? There's like TCP and UDP. UDP is like what you use for Zoom, right? So that's why I'm like covered in UDP packets. So we're probably not going to see anything interesting. This is all Zoom stuff, I think. Yeah, so it's basically sending it from my computer to the router. So it's pretty. You could like catch all the packets that are going to and from your computer. I think if you look carefully, you could probably see my TCP connection with Facebook. Is it? I don't know, but yeah, basically like you could like it's not that hard to find all these packets. So essentially, the reason why people still can't see your messages, even if they get the packets, is because it's encrypted with this thing, and only the person with the decryption key can actually see what it is.
Oh, and a fun fact for what UDP is. Basically, it's it's similar to TCP in the sense that it operates on the transport layer as well, except it's less secure. So not less secure, it's less good term for
Resilient
it.
to failure, yeah.
Yeah. TCP will make sure remember those acknowledgement requests and making sure everything's in order and whatnot. TCP will resend things and UDP won't. So for something like Zoom, when you're live, you don't want to be held up. If you lost a packet that's in the past already, you don't have to worry about it anymore. So that's why you would use UDP for something like live.
Yeah, because you don't even care with the order. As long as some of the packets make it, as long as you could get like some of the frames so I could see that you're moving, I could see that you're talking, we're good. We don't actually need to make sure that every single packet is in order and every single packet gets here.
Yep. Okay, asymmetric encryption. Right. So basically, The key here is you have two different keys. You have the public key and the private key. The public key allows you to sign documents and encrypt, and the private key allows you to decrypt. And the main point of this is that the ability to encrypt does not automatically confer the ability to decrypt, and that's really important.
Does anybody know a very famous form of asymmetric encryption? Come on, you just guess an encryption and you will probably get it. Nobody knows any encryptions whatsoever. Seriously? Okay, Albert, you better tell us. You know this. You know this. Come on, Albert. No?
No idea.
Come on, just guess an encryption. Fine, what's one that uses prime numbers? How about that?
RSA?
Hooray!
encryption?
RSA is a very good example of an asymmetric encryption algorithm, right? Because basically you publish your public key, which is like some number, number to a prime number, right? And then somebody else takes it to another prime number, and then only the person with the original prime number can get back the actual thing that you took to the power of the prime number. So like essentially the idea is anybody could encrypt it, but only one person can decrypt it, which is why it's really useful for websites, right? Because everybody's accessing the website, but only the website should see what you actually wrote to them.
But that's based on the fact that it's easy to go one way. It's a one-way operation because you can take the power to a really large prime number really easily. But to find out what the prime number was in the beginning, to find out what that key was, that's near impossible. Okay, the SSL certificates that make sure the server is who they claim to be. So it's a document that consists of the public key that's assigned to the server. And these are issued by certificate authorities, and they can also verify SSL certificates. And again, this is authentication. It verifies that you're getting the right public key from the server that you want to talk to, and that will prevent you from getting hacked. And here's the man-in-the-middle attack I was talking about. Here you're talking with the server, you're exchanging information. And over here, the man-in-the-middle claims that they're the server. And they'll be taking the information from both sides. So that is, that's an attack easily stopped by SSL certificates. And here's the meeting flag. You can send it in the chat, right?
Oh yeah.
Okay.
Oh, there's like another interesting thing to think about. Like so basically, if we know how like we could use RSA encryption to encrypt stuff, right? To make sure it's like not readable to anybody else. But does anybody have an idea for how you could use it to sign things? Does anybody know? Like how could you verify that something is signed by a specific person if they have the private key? So essentially only one person should be able to sign, but everybody else should be able to verify. Does anybody have an idea? It's kind of interesting. Wait, yeah, Mason, if you wait, could you? Okay, I'll send. Or wait, could you send it to the chat if you have it?
Yeah, I'll send it.
Does anybody know? Well, essentially, what you could do is you take the message, and then you include the message encrypted with your a private key, right? And then everybody else just make sure that like the public key is like the decryption key. So they just make sure that the thing decrypts to the original message, and then it's pretty cool. So then that is how you make sure that it's coming from the right person. Okay, well that is all we got for today. So any other questions or well, if you don't have any questions, feel free to dip. But thank you guys.
By the way,
oh yeah, wait.
You can search up. Again, this is probably not very accurate at all, but if I take my IP and search it up, it gets a pretty good estimate of where I am because of my internet service provider.
Oh, I see.
So, yeah.
Okay, sounds good. Thank you guys for coming. Feel free to